Okay, and we are recording. So hello, everybody. Welcome to another seminar for the Explainable Fuzzy competition. This week, we are joined by Dr. Scott Dick from the University of Alberta to talk about fuzzy logic and explainable AI, past, present, and some thoughts on the future. To give a quick background on Dr. Scott Dick, he did his BS, MS, and PhD, all from the University of South Florida. His dissertation received the USF Outstanding Dissertation Prize in 2003. He was an assistant professor from 2002 to 2008 and from 2008 to 2018 with the Department of Electrical and Computer Engineering at the University of Alberta, and was the program director for computer engineering for 2017 to 22. He's published over 80 scientific articles in journals and conferences, and is a member of ACM, IEEE, and ASEE. His research interests are broadly in areas of computational intelligence, fuzzy logic and neural networks, machine learning, data mining, as well as the application of these technologies, interdisciplinary application of these technologies. His main theoretical interests are in multi-valued logics, particularly the new area of complex fuzzy logic, deep learning approaches based on those, and explainable artificial intelligence, which we're going to hear more about now. So, Scott, over to you.
All right. Thanks very much, Tim. So, good morning, afternoon, evening, whichever it might be in whatever locality you're joining us from. Makes things a little bit difficult to tell what to say when you're remoting in, but that is the modern world for you. My name is Scott Dick, and for my sins, I am currently a professor at the University of Alberta in the computer engineering department. Today, what I'm going to talk about is how fuzzy logic and explainable AI relate to each other and have related to each other throughout the history of the two fields. And also a few thoughts about how the future might look. So, before continuing, I'd like to start by thanking the XFC 2023 organizing team for inviting me to present this talk. I hope you will find this a helpful resource for the competition. To all my friends and colleagues in fuzzy logic and computational intelligence, this has been a warm and welcoming community ever since a wet behind the ears PhD student showed up to his first conference at Fuzz IEEE in San Antonio back in 2000. Thank you for all the conversations, advice, and questions throughout these last 22 years. And of course, to my students for teaching me so much. In particular, this talk is based on work I've done with my PhD student, Martaba Yaganaju, and especially the chapter we have in Plamen Angelov's forthcoming Handbook on Computer Learning and Intelligence. So the place I always start in my research is the value statement. Why should anybody care about what we're doing? Well, the economics of AI make a pretty compelling case. According to one study, 50% of all the tasks that make up jobs in the North American economy could be automated. That doesn't mean eliminating the job. It just means that elements of the job could be automated. So about 95% of jobs can be made more efficient by through optimizing them through using AI. This is a major path that is supposed to push productivity growth back up above 2% per year, which it has fallen below in recent decades and which worries economists a great deal. And if it all pans out the way the study authors think, it could add between $3.5 to $5.8 trillion per year to the North American economy just by itself. I don't know the numbers for Europe, but you're probably looking at something similar. So AI is great, right? Well, then you get into the big question. Why should we trust an AI? Modern neural networks are black boxes, and their decision-making process is opaque, sometimes to the point of being incomprehensible to a human user, even an expert. So in the 2016 Go match between Lee Sedol, who's a grandmaster, and Google's AlphaGo, one of the moves, the 19th, was called Creative by a Go expert named Michael Redmond. And his comment was, "It's something I don't think I've seen in a top player's game." So the AI came up with something that masters and grandmasters just don't do on the way to actually beating Grandmaster Lee Sedol. The thing is, though, we don't know why. We don't know what's going on in the deep layers of a convolutional neural network or a stacked autoencoder or a belief network. This raises the rational concern that an AI's next move, even if all the preceding moves were quite sensible and effective, what about the next move? Is it going to be something that is unexpected? Could it be harmful? Could it lead to the loss of property, life or limb? All, the things that engineers are really concerned about. We just don't know, and that's a very large problem. Phrased another way, are we wandering into an area of the state space that the AI has not been carefully trained on? We also have to acknowledge that when you're facing an AI, there's the fear of the unknown as well. Not a rational response, but you have to understand that humans are not rational beings at our emotional core. And that's part of being human, and therefore the irrational response of fearing the unknown is still a legitimate and realistic problem that AI designers must deal with. Simply put, if human users don't trust AI for whatever reason, be it a rational thing we can deal with or just an irrational fear of HAL 9000, humans have the sovereign right to just walk away from the AI revolution. That can happen. It has happened. The AI winter of 1987, the two neural network winters of the 1970s and the late 90s to early 2000s, those are historical events. They could happen again unless we do something to stop it. So obviously, that something is we need to improve the trustworthiness of AI. So what does that mean? Well, back in 2019, the European Commission's high-level expert group on artificial intelligence developed some guidelines for developing trustworthy AI. These are ethical principles that should be applied throughout the development cycle and on into the use of the AI. In other words, whole life cycle. So respecting human autonomy, preventing harm, fairness, and explicability. So the last of those, explicability, the ability to explain, that's what we're focusing on here. But it's fair to remember that all the others must also be present. And in fact, explicability can give life and effect to the other three principles. How do you know that the AI is in fact respecting human autonomy and not just accidentally giving good responses for a few initial cases? Well, by actually looking at what the AI is doing and why. And for that, you need explanations. Fairness, same thing. But coming back to explicability, it's rooted in the right of an EU citizen to contest a decision or action that impacts them, whether from a public or private entity. It might be an administrative complaint. It might be a legal suit, etc. But the ability to contest is absolutely fundamental to what we think of as freedom in the Western world. Now, in order to exercise that right, you have to be able to demand an accounting of what the decision that affected you is and why it was reached. And if that accounting has to come from an AI, the complainer must be able to understand the explanation. That is explicability. Also from the EU, the Data Protection Directive contains the right to an explanation. Citizens must be able to receive an accounting of any algorithmic decision that is made concerning them. And again, it must be understandable. Beyond just the legal requirements, when you look at the literature on trustworthy AI, one thing that stands out is how important explanations are. It's not just a right. There's a whole bunch of studies going back several decades showing that human users are more willing to trust an AI's decisions if they can be explained to them. In other words, the act of explanation, the ability to receive explanations, is fundamental to the question of trusting in AI. Now, in the last two slides, I've thrown the word trust around a lot. And as humans, we understand it intuitively. But when you try and break it down into something that can be engineered, you suddenly realize just how big of a word trust actually is. It actually touches on almost every aspect of human existence as social creatures. And there are many, many definitions from all sorts of different fields. But at their core, every definition I've seen centers around the choice to make yourself vulnerable. In other words, I'm going to trust that when I open myself to being hurt, the person I am trusting will not hurt me. We might make that choice based on a calculation of legal constraints or cost-benefit reasoning. This person will go to jail if he steals from me. Or this person is going to wind up getting sued and owing me a lot of money if he breaks the contract. And it's much cheaper to just go ahead and honor the contract. This is an assessment based on logical reasoning. It can also be based on an emotional connection. I trust my family that they are not going to literally stab me in the back. Now, if your name is Julius Caesar or some other figures in history, maybe that's not the best assumption to make. but I certainly feel comfortable with it with my family. Not because there's a cold, hard reasoning, but because I love them and trust them. There is always an element of risk, whether you've made an assessment or just feel an emotional connection. Probably not too much of a risk, but there is a risk. In fact, if there's no risk, a lot of the literature argues that that's not actually trust you're extending. And now we see why explanations are so vital in AI. The AI is not a person with goals, values, and desires that we can evaluate. It's a hyper-complex mathematical function that performs one task very well. That's what it is. There's nobody there. No actual person we can form a bond with. It's an empty suit that gives the impression of intelligent behavior as long as you stay within a very specific domain of expertise. Trust in an AI means users have to assess the fit of this mathematical function to their needs and do so within the limits of human cognition, and likely without any specialist training in AI. And make no mistake, we are already vulnerable to AI decisions, and the entire roadmap for the future is to become more so. Current AI designs have already done harm. Prison sentences, loan and insurance approvals, hiring practices. AIs have been deployed in all these things, and they have produced some very unjust outcomes. And when I say unjust, I mean unjust in the sense of violations of what's called natural justice. The intuitive sense we have as a society of what is a proper outcome, what is a just outcome. And a lot of that traces back to data bias. You've probably heard this term batted around. Data bias is the idea that biases in society, racism, sexism, ageism, all the other isms that we worry about, aren't explicitly coded into an AI. No one would do that. But the source documents that you use to train the AI, newspaper clippings, images scraped from the web, or anything scraped from the web, it contains within it, implicitly, latently, the biases prevalent in society, and especially the biases of the person who created each artifact that we're training on. And does this actually affect the AI? Absolutely, yes. We see lots of racist and sexist biases in decisions made by AIs that if a human had made them, somebody would get sued. And people would be on their Facebook pages screaming at them. But because the AI is machine and theoretically unbiased, it has gotten a pass until something blew up. So explanations are expected to be a major means of countering AI biases, since the AI will not attempt to prevaricate. If it has determined through its training that Black Americans should receive a smaller loans than white ones, then it should flat out tell us that. Not try to hide it away or make excuses. It'll just say, homeowner is Black, so lower score. unjust, but at least the AI should be honest about it if we have an explanation from it. So let's start talking about what an explanation would be. Well, we have two words, opaque and transparent AI. We throw them around a lot, but what do they actually mean? So at the level of philosophy, Zednik in 2019 argued that an AI has quite a large number of what he called epistemically relevant elements. In other words, things that could be cited in an explanation. These include input values, their distributions, details of the AI algorithm, and how it was trained, internal calculations made for a given input, the outputs for a given input, so on and so forth. Is each of these equally likely to everybody? Probably not. Different epistemically relevant elements will be of greater or lesser importance to different stakeholders in the AI. So AI developers will have a different opinion about what's important versus government regulators versus lawyers looking to file a lawsuit against the developers, ordinary users, so on and so forth. So in that sense, opacity refers to an observer's lack of knowledge at a point in time about some epistemically relevant elements that they deem important. The less the observer knows, the more opaque the algorithm is. The more they know, the more transparent the algorithm. So explanation's purpose is to reduce opacity by communicating epistemically relevant elements to the observer in a way that makes sense. Now, when we say communication, we specifically mean a social act. Explanation has been very heavily studied in a number of fields for hundreds of years, basically. So this framework that I'm putting on the slide is the one that was used in Miller's paper on XAI in 2018. You can find that in Artificial Intelligence. It's a long paper, but very, very, very good. So you have two social actors, an explainer and an explainee. Classically, both are human. There is something that the explainer understands better than the explainee. He's going to try and convey that knowledge. The thing that the explainer understands well is called the explanandum. It is the thing we are explaining. The knowledge communicated from the explainer to the explainee about the explanandum is called the explanans. So the key takeaway here is an explanans is the actual explanation itself. The explanandum is the thing we are explaining. Now you notice that I had a two-way arrow here, and that's what I mean by this being a social act. The explainee can communicate in a variety of ways where they need additional clarification. In other words, how do we further clarify the explanans beyond what the explainer initially presented? This is why you think of explanation as a social act. It is the interaction between these two persons, their communication back and forth, that ultimately produces understanding. In teaching, we call this active learning. It's well known. In a variety of other fields, this holds true as well. The question, however, is this: how do we construct that social interaction when an AI is the explainer and the AI's own decisions are the explanando? How do we produce an explanans that is an effective communication, but also allow the explainee to request further clarifications? Pretty obviously, this needs to actually be a major element of system functionality. And it's been done. I'm going to call this generic functionality the explanation interface for the rest of this discussion. Like I say, they have been studied for a long time, since the 1970s, actually. So quite a few people have written about what should be the design goals of this explanation interface. We'll just call it an EI. So 1993, Swartout and Moore proposed these 5 characteristics. Fidelity. The explanans needs to reflect the actual processes that were used to reach a decision, not just something made up. It has to be truthful. Understandability. Your system's users have to understand the explanation you give them. Sufficiency. The explanans has to provide sufficient detail to justify and defend the system's decisions, possibly even in a court of law. Low overhead. The development effort invested in the AI should only be proportional to the total development effort of building the entire AI system. After all, the EI is just a part of it, and it's not the part that actually does the work. Efficiency. The execution time for the AI overall should not be unduly increased by including an explanation interface. Of course, the difficulty in all this is that some of these goals conflict with each other, especially for large-scale AI. So about 5 years ago, the BERT network was the biggest thing out there. It no longer is. It's relatively small, but it was the first really large transformer-based architecture that had breakthrough performance in natural language processing. So it's a transformer network with 345 million parameters. So a fully sufficient, high-fidelity explanation for this thing, like, for instance, an extracted rule set, will be monstrously large. Well, there goes understandability right out the window. Monstrously large rule sets, even if they're in English, are just not understandable. Time complexity for rule extraction is another problem. Every rule extraction algorithm I've seen is super linear in time complexity. 345 million parameters. With a superlinear algorithm, that is going to be a lengthy process. And you can't pre-compute it because it's a pre-computed rule set will not have high fidelity or sufficiency. There are other more recent proposals. Here's one from 2017. And now the design goals are fairness, privacy, reliability, robustness, causality, usability, and trustworthiness. So quite a lot of a change. So we know we need explanations. People have been talking about them for quite a long time. how does it play out in the history of AI? So I built this figure based on information from Nils Nilsson's book, The Quest for AI, which is quite an interesting read. It's a very personal history of especially the development of symbolic AI, what Nilsson calls good old-fashioned AI. And it basically is about the split between symbolic and non-symbolic AI. So let's admit up front, one figure will never capture the whole history of AI. It just won't. I built this figure to pick up a few of the most important developments in AI on the symbolic and non-symbolic sides, and to illustrate kind of when they were happening and how they kind of clumped together. So symbolic AI, it refers to systems constructed around some form of expert knowledge, which plays a very large role in the design of the system. So they were talking about theorem provers and expert systems. Fuzzy sets of logic also belong in that group. So these algorithms are relatively easy to interpret and explain. And many of them, Myson and its descendants and things since then, have tended to have explanation interfaces built into them. In fact, Neomycin and Explain in the early 1980s were part of a second generation of expert systems that were distinguished by the attempt to improve the quality of their explanations. So non-symbolic approaches are computer algorithms that excel at some task that we believe requires intelligence, but which may bear little or no relationship to how humans actually think. So this includes things like statistical machine learning, so hidden Markov models, like the Dragon model of 1975. That there's no hidden Markov model in a human mind, but they have been a very powerful approach to speech recognition. Similarly, Mikula-Petz neuron and its various descendants are inspired by a biological neuron, but nobody at all thinks that there is a backpropagation algorithm running in our brains. So non-symbolic AI has a tendency to be somewhat more accurate, but also much more difficult to interpret or explain. And that's one of the themes that emerges. The accuracy interpretability trade-off, which we've talked about in fuzzy logic for decades now, is also a major issue in general AI. Everybody keeps finding that the most accurate algorithms are highly opaque, and the more transparent algorithms are less accurate. And this also feeds into one of the themes you can kind of see from, if you look carefully at the symbolic versus non-symbolic approaches. There seems to be a vacillation between symbolic and non-symbolic AIs. People have gone back and forth repeatedly about which one is going to produce better results. I haven't really included anything in symbolic AI beyond the AI winter in 1987, simply because the machine learning algorithms just around then just outran the classic AI approaches, which is not to say they don't exist, and it's not to say that they may not come back yet again. So where does fuzzy logic fit into all of this? So for the remainder of this talk, I'm going to look at 4 areas in which fuzzy logic has contributed to explainable AI. I'll start with rule-based systems, that's fuzzy inferential systems, and then I'll go on to fuzzy expert systems, which is a different topic. Then I'll look at neurofuzzy systems, and finally, the more modern deep neurofuzzy systems. And as a part of this discussion, I'm specifically going to look at the question of how explanation interfaces were implemented. So first things first, fuzzy inferential system. What's in every textbook and what we all learn about first. They are rule-based inferential systems, most commonly used as intelligent controllers. Plainly, they're a feed-forward system. So all the knowledge present in this FIS is encoded in the fuzzy rule base, which is a collection of fuzzy rules. This particular design is the Mamdani FIS, for which the antecedent and consequent clauses are all fuzzy sets. In order to interact with an electronic control system, however, we need some pieces that go around it. The inputs to the FIS have to be fuzzified. They have to be transformed into fuzzy sets of their own. That's the fuzzification interface. Those fuzzy inputs are then combined with fuzzy rules in an inference engine. That produces a fuzzy output, which then has to be defuzzified, usually with the centroid defuzzifier, producing a crisp output that we can pass on to a controller. Now, why is this interpretable? Well, the key is here. Linguistic variables. So at the very bottom, you see a canonical Mamdani fuzzy rule. If variable x is small and variable x and variable y is big, these are the 2 inputs, then output z is large. So it's a linguistic rule. It's fairly understandable once you fill in what does x, y, and z actually represent. Could be very many things. Mathematically, it's given meaning by associating each word with a fuzzy set. And the structure that does that is a linguistic variable, which is a 5-tuple. X, the name of the linguistic variable. U is its universe of discourse. T, the set of linguistic terms for the linguistic variable. These are the values it can take. S, syntactic rule for generating terms in T. Now, most commonly, you've probably seen term sets that were just static lists of 5, 7, maybe 9 terms. You can also have hedges that modify those terms, and then you'd have basically an infinite number of them. In general, the syntactic rule for generating terms in T is a context-free grammar. And these were all worked out in a series of papers by Lofty-Zada in the early 1970s. And finally, M, our semantic rule, associates each term in T with a fuzzy subset of U. This is how we give a precise mathematical meaning to these English words. That's what the linguistic variable does for us. So great. We have English words. So easy to construct an explanation interface, right? Except we don't. In most literature in fuzzy systems, you find that it is simply said that the rules are intuitively understandable, and then the paper stops. You do not continue on to actually build a true explanation interface. And that is actually a serious weakness. There's been lots of research on this kind of explanation interface, and it has been found lacking. These results go back all the way to Mycin in the 1970s. There's no social act of explaining here. There's no way a user can make more queries. Now, an FIS is rule-based, but it's not an expert system. Both do use rules, yes, but an expert system is more than just a rule base. So here we have the basic diagram of what an expert system architecture is. This is called an expert system shell. You have a rule base, absolutely. And you put your rules in here for whatever domain you have. There's an inference engine that will actually work with the rules. Sure, absolutely. And then there's this thing called working memory. You receive your input data here, yes. But you also have the conclusions from every rule that has been fired up to this point. This combination of things is called the set of facts. And then you have rules that may yet be fired. So a rule is fired when its antecedents match what is observed. Okay. So we have a whole bunch of facts in working memory, and we have the rules that have not fired yet. They are together called the conflict set. And now we have to match facts against the conflict set. Not easy. Generally, this problem is called the many patterns, many objects matching problem. And a brute force approach to solving it is exponential time complexity. Obviously not good. Most every practical expert system uses an algorithm called the REIT network, which arranges the conflict set as a tree. And that lets you solve the many pattern, many object matching problem in polynomial time. So, something completely reasonable. So that's one of the key things that is actually a characteristic of expert systems. The ability to add facts to the working memory as you reach conclusions, and then the ability to use those conclusions to fire additional rules and create more facts. Maybe even circle around and add facts back in. It's hard to say. So that's the working memory. And you'll notice there is an explanation interface in most expert systems, ever since Mycin, which is 1975. Now, one of the things that it was a weakness in Mycin, they used a thing called uncertainty factors, which basically represented how sure you were about a given fact or a given rule. But they were not based on any probabilistic or possibilistic mathematics. They were just a number assigned, which meant that every time you added a new rule to the rule base, you had to very carefully adjust the certainty factors of every other rule so that conclusions that are formed had correct and consistent certainty factors, because it was all just ad hoc. So, okay. Of course, Zada spotted this and proposed that a fuzzy expert system would have a couple of advantages. Number one, linguistic rules would more naturally represent knowledge. And number two, those certainty factors, if computed with possibility measures and the compositional rule of inference, would be more robust, and they would be naturally self-consistent. So you wouldn't have to go around readjusting and twiddling every single certainty factor in the entire rule base when you added one new rule. So people took note, and in the 1980s and early 1990s, there were quite a few fuzzy expert systems proposed. Some of the best known would be fuzzy clips and fuzzy shell. And they're both algorithms that employed REIT networks in their working memory. And they had possibilistic certainty factors, and everything was quite good. But again, there was no attention paid to an explanation interface. When I dug into it and went looking, I actually only found one fuzzy expert system shell that it actually included an explanation interface. It was done by Leung et al. In 1989. Fuzzy clips and fuzzy shell, the two best known, nothing. Okay, Neurofuzzy Systems, which is the stuff I tend to do in my own research. So they came up in about 1991, a few years before the second neural network winter hit. And honestly, I've always seen them as drawing some inspiration from the knowledge extraction approach to generating explanations from neural networks. So you fundamentally have two distinct approaches. Fuzzy neural networks have come to mean directly substituting fuzzy quantities or operations into an existing neural network architecture. And a main goal is usually explicitly to make extracting the knowledge from that neural network easier. The resulting architectures are somewhat more transparent and tend not to lose very much accuracy at all. But again, they're only somewhat more transparent. A very low level fuzzification of individual neurons doesn't do a whole lot for transparency, because it's the pattern of interconnection weights in the neural network that contains all the knowledge, not the individual weights themselves. Neurofuzzy systems, applied here in a very narrow sense, are specialized neural architectures that try to mimic a fuzzy inferential system. So the picture on this slide is ANFIS, probably the best known representative of this class. Its design mimics Takagi Sugeno Kang fuzzy inferential system. And that's the variation where your consequent is a mathematical function, usually a linear function of the inputs. It's a close enough mimic that you can actually read out the TSK rules fairly easily. With one caveat, the parameters of your fuzzy sets in the first layer, where you have that membership function that looks like a hat, those parameters are adaptable. So the fuzzy sets at the end of training might be radically different than the original prototypes that were given linguistic names. Another thing, the TSK fuzzy system and ANFIS are known to be universal approximators, but that is kind of a existence proof rather than something more practical. TSK outputs are linear and combinations of linear functions. So you can approximate any given curve with a set of linear segments, but you might have to make those linear segments very, very small. In other words, a huge number of rules to achieve a given target level of approximation. So an ANFUS of any practical size is normally less accurate than a fuzzy neural network or a crisp neural network. You might notice that the same criticism could be applied to deep neural networks running ReLU, rectified linear unit activations, but that's a whole other discussion. And again, explanation interfaces are not usually a part of these systems. Knowledge extraction is just getting the rules and presenting them as a static list. It is no communication, no ability to query. Now we come to modern XAI, which focuses on explaining deep neural networks. And it reuses actually quite a few of the tricks from earlier shallow neural networks. There are rule extraction interfaces out there and so forth. But for convolutional neural networks, at very least, one of the most common approaches to explanation is a visualization called the saliency map, which is built by things like layer-wise relevance propagation, which is LRP in the second line. Or you might build a model that is easier to understand, but mimics the deep neural network. That would be Lime and Shep. All of these are post hoc explanations. In other words, they're attempts to account for what the neural network did without actually making the neural network more transparent. So deep neurofuzzy systems again try to make the neural network itself more transparent. And it again follows the same kind of pattern. You might have a deep fuzzy neural network, which substitutes fuzzy quantities into an existing architecture. Or you might have a deep neurofuzzy system, which attempts to mimic your something that looks like a fuzzy inferential system. So I'll look at two examples. Fuzzy restricted Boltzmann machines as an example of fuzzy neural networks, and fuzzified classifier components in the second one. The latter is actually my student's work, as an example. So here's a restricted Boltzmann machine. It's a two-layer network, one externally visible, the other one hidden. And they're trained using a statistical algorithm from Markov decision processes called Gibbs sampling. So the two layers are densely connected with numeric weights. And the weights are what we're going to train. The fuzzy restricted Boltzmann machine replaces the numeric connection weights with fuzzy numbers. Simple enough. So a learning algorithm for this fuzzy RBM was tested, and it was found to do better than a classic RBM. That was 2015. And then in 2020, we pulled the stacking trick. So a visible layer in the visible layer was replaced with a new Boltzmann machine, so a hidden and visible layer, and retrained, and this just kept stacking and stacking, which is the way that you build a deep belief network out of a regular RBM. So what we ended up with when we stacked the fuzzy RBMs is a fuzzy deep belief network. So, and when it was tested on 4 benchmark image data sets, fuzzy DBM outperformed the classical DBM and was more robust to noise. So the second group, which includes my students' work, in the convolutional neural network literature, you make a distinction between the convolutional component and the classifier component. First part is your convolutional and pooling layers. And this is the automated feature extractor. This is where all the power of the CNN is. Because it then feeds to what are called dense and softmax layers. What are these? It's a multi-layer perceptron. One or more hidden layers densely connected of perceptron neurons feeding to a softmax classifier layer. Well, that's a classic shallow neural network all on its own. So our thought was, okay, the classical neural network itself is a black box, throw it out and replace it. We did a fuzzy classifier based on clustering followed by the nearest prototypes algorithm. Simple. And then our explanations are the medoid element of each cluster. So when we actually tried a pseudo EI approach, so a pseudo explanation interface, we present the medoid of a correct classification and the misclassification that was made versus the actual image that was misclassified. And we superimpose it on the two medoids. And what we found was in the MNIST data set, you actually wound up with very sensible, rational decisions. If a 6 was misclassified as a 0, when you looked at it, there was a lot more overlap between the important pixels of the 0 medoid rather than the 6 medoid. So it was sensible. But again, that's not a true EI because it's not queryable. And in our current research, we're looking at using ANFIS as the classifier component and how the performance changes across when you have different convolutional components, like from LeNet or ResNet or wide ResNet. We're exploring quite a few. And we're finding that our performance, at least, stays about the same. So where to next? It's noon, so we'll wrap up here. So how do we actually build explanation interfaces? Quite a few authors recently have pointed out that good explanations among humans involve generating and reasoning about counterfactuals, things that did not happen. It seems reasonable that creating a counterfactual from a DNN from a deep neural network is difficult. What didn't happen is not encoded in the weights. However, if you have a deep neurofuzzy system where the rules you extract do actually relate to events that happened, you can reverse those rules just by applying a negation to generate a counterfactual, and then reason about that. Also, an important point, gold standard research in XAI, especially after the DARPA XAI project's final report, insists that explainability be evaluated through human trial research. There's no automatic way to determine how explainable a given explanation is, how good a given EI is. You have to, in the end, you have to use human trials to evaluate an EI. And this ties back to all the human factors research that is done in computing science. You cannot determine usability or ease of use or any other attribute involving humans without actually involving humans in your evaluation process. So my feeling is the building of EIs needs to become a major element of the fuzzy systems community. And if we're going to go down that road, we have to get deep into using human trials to evaluate those EIs, because nothing else is really acceptable anymore. And that is the end of my talk. So I'm open for any questions. Wow! Tim, on my screen, you just kind of teleported in, just kind of faded in. Yeah.
Oh, I'm
It
sorry.
was a cool effect, but man.
Interesting. That was not my intention. Well, I guess since I have your attention, I'll go ahead and go first with the questions. I was curious, you know, you spoke quite a bit about using explanations as a way to increase humans' trust in AI. How do you square that with the V&V process that typically goes for these types of systems? Specifically, you know, my thoughts are towards, I would say, formal verification, simply because if you can prove adherence to requirements or behavioral specifications, do you need explainability?
Well, let me throw it right back at you. You have your formal proof of correctness. You walk into court with it and slap it down in front of the judge. What does the judge say to you? Does he
How
say,
do you know that that is a proof?
uh-huh.
Yeah.
Yeah. So explanation is not just about mathematical proof. Mathematical proofs are well and good, and for an AI system designer, that may in fact be the right explanation. That may in fact be the right explanans to give, or an AI tester. But that's not the only, those aren't the only stakeholders you have. And in fact, realistically, in a lot of ways, they're the least important stakeholders. Your users and any government regulators or public watchdogs. To a very large extent, they may be more important users who will simply look at a formal proof of correctness for an AI is going to be thousands of pages of math. And they're just going to look at it and go, I have no idea what that said. Now, explain the AI to me.
Yeah, very good. I tend to agree that yeah, getting explanations, I guess the relevant explanations based on the explainee is, yeah, that's a big problem.
Theme I've been pushing in some of my grant proposals recently. An EI is itself an engineered construct. What's the first thing you do in building an engineered construct? Identify the needs of your users. And more specifically, the needs of the stakeholder groups you're going to produce this explanation for. So who are you explaining to? How are you explaining? What do you intend to explain? This is something that has to be thought of at the design level.
Yeah. Yeah, that's interesting, and yeah, I agree.
Mm-hmm. You don't see a lot of this in the AI literature. It kind of gets glossed over. Just people saying explanations are good, you should have them. But there are a few papers that have actually thought about this and come to the conclusion that, yeah, this is something you actually have to engineer for any kind of practical use.
Right. Well, thanks for that.
Mhm.
I'd like to invite others to ask any questions they might have.
Peter,
Hi, Scott.
how you
How are you
doing?
Good. What's up? So, don't you have to be very close to humans? Don't you have to have sort of like a human-computer interface? And you have to be able to understand the language of humans. So you can't like translate things into machine language, but it has to be like human language.
Oh, yes, that's a big thing about a queryable interface. You have to be able to process a query into some kind of thing that the explanation interface can actually pull out of the AI. So the humans just simply typing what has to be turned into some kind of a set of operations. And that is the fundamental process that the EI is going to have to do. Now, the good news actually is that in the literature, what we find is there's a fairly limited set of canonical questions. What did you do? How? What if? And especially when, but what if is really the important one, the difficult one. That's where you need to generate counterfactuals, because the what ifs are usually questions about things that didn't happen.
So when you talked about the counterfactuals, am I right to assume that you just said, well, this and that didn't happen, right? So
but what if they did?
Yeah, not A, then not B. So that's kind of like what you're thinking about.
No, you can't think of it that way. What you have to think of is assume out of action set A, B, C, D, E, the AI chose action A. Your counterfactual has to cover what happens if you choose B or C or D or E or F.
Mm-hmm.
And because all of those may be different things, and combined with other action sets in different parts of the decision of the process, all the possible combinations of what action sets were taken
But you
are
always
things you have to be able to answer about.
it is always, about actions. The machine, if we got an input, then the machine acts this and that, or you're supposed to act this and that, to do this and that. It's isn't that different from like let's say, well, if this is true, then this and that is true. So
well, in theory, it's the same sort of thing, because you would use the AI to simulate the possible other action states and come up with an answer of what would have happened.
Yeah.
So you would basically you would take your trained AI and you would fire an input through it that matched a counterfactual that you had generated.
So then if you generate a counterfactual, then you generate a new rule.
Well, it might be, depends on exactly what your AI was. But if we're talking about a neural network, like for instance a CNN, a counterfactual would basically represent a set of inputs that did not happen, but which could have. So you would have a different set of inputs. For instance, you classified this picture as cat, but what if I give you a picture of a tree? What happens? So in that case, you would generate an input that is tree, and you fire that into the CNN, and you see what comes out the other end.
So maybe what you're actually doing with your counterfactual is so you're going the other way around. So you're going like, you know, instead of going in one direction, you're going in the other direction with the counterfactuals. That's how you use the counterfactual.
Oh, I see what you're saying. So what if you asserted that we have class tree at the end, and what does that make the inputs look like?
Yes.
Yeah, well, you know, you would probably try to tackle that with some sort of saliency map approach. So there's lots of them: layer evidence propagation, guided back propagation, some way of taking the fact that this is class tree, and then you back propagate to the inputs and find out what are the relative importance of the pixels in making that decision. Now, normally this is done with an actual classification. So what typically happens is you get a heat map that does actually resemble the original image, with certain pixels being the most important. Very often we find that the pixels that are seen as important are really stupid choices that makes us not trust the AI very much, but we at least see them. When you're backpropagating from a wrong class, from an arbitrarily chosen wrong class, then I can imagine things might get very strange. Because if you're saying, I know that this was correctly classified as cat. Now I'm going to say that it is actually chocolate bar. What would the pixels that are important to making that classification look like, please? And you're going to get something really weird coming back out. But perhaps that weirdness tells you something useful.
And do you also work with antonyms, since you're...
I have not yet really started that. That is, however, going to be in my operating grant proposal that I'm writing right now.
Okay.
So yes, that is an objective, and actually I'll be citing the paper you and I wrote about that as evidence that this approach might be well be an effective way to go.
Okay, let me ask a last question. I didn't get like what the explanation could be in your fuzzy Boltzmann machine, because then you have fuzzy weights.
I didn't talk about an explanation from it at all. I simply pointed out no explanation interface was built for the thing.
Could there be one?
I don't really know. I haven't done a lot of work with the Boltzmann machine classes and the deep belief networks, so I'm not deeply familiar with how they work. I know it's Gibbs sampling, and I went through it once about 4 years ago in my neural networks class, but I just don't remember the details too clearly.
And did you get far ahead with your query interface? You know, with that interface, because you didn't lose many words about this. You know,
No, because we haven't really built a true AI. We've explored the thought of using cluster medoids as your explanans, and in the MNIST dataset, it seemed to work quite well, course, MNIST is really simple. And we're currently looking at how well it works in the fashion MNIST data set. And that paper is almost ready to go out. But as far as actually building a true queryable EI from that insight, no, we haven't gotten there yet.
Okay, thanks.
Yeah, no problem. Any other questions?
Yeah, does anybody else have any questions for Dr. Scott Dick? Going once, going twice. All right, well, I'll return the remaining 12 minutes to everybody's day. Thanks again to Dr. Scott Dick for coming to talk with us about explainability in AI systems, and more specifically fuzzy.
My pleasure. Thanks for having me.
Yeah, thanks again. And we'll be talking to everybody soon. Reminder that the recording for this will be up on our YouTube channel shortly. And a reminder that we will be getting talks from Dr. Barnabas Bede in the next coming weeks on gradient descent in fuzzy systems, and also reinforcement learning, gradient-based reinforcement learning. So those should be very interesting. All right, thanks everybody, and have a great day. Bye.
All right. Thanks for attending. Goodbye.